Beautiful, 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 beautiful angel. Love your imperfections, every anger. Tomorrow comes and goes before you know. So I just had to let you know the way that Gucci look on you.
Orthonormal basis. A set of vector space V is said to be an orthogonal set if every pair of vectors in the set is orthogonal. The set is said to be an orthonormal set if it is orthogonal and each vector is a unit vector. Let V is a subspace of real numbers. S is an orthonormal set of vectors if ui times uj equals to 0 for I not equivalent to j. Second one, the unit vector of u, which is square root of u square, equals to 1. To explain more about the definition I've told, let's look into example 1. Show that the set stated is an orthonormal set. We solve this by finding the unit vector for every vector in the set. We find the unit vector by square rooting the summation of squares, and we repeat for every vector in the set. We get the unit vector equals to 1. This shows that the vectors are unit orthogonal vectors. Thus, the set is an orthonormal set. Theorem 1. Let a set of vectors consisting u1 up to un be an orthonormal basis for a vector space V. Let V be a vector in V. V can be written as a linear combination of these basis vectors as follows. V equals to V times u1 multiplied with u1 plus V times u2 multiplied with u2 until V times un multiplied with un. To prove the theorem 1, let's look into example 2. The following vectors u1, u2, and u3 form an orthonormal basis for R3. Express the vector v 7, -5, 10 as a linear combination of these three vectors. To find the linear combination, we must find v times u1, v times u2, and v times u3. Then, express v in terms of linear combination of these three vectors. So we get 7, -5, 10 equals to 7, which is v times u1 times u1 plus v times u2, which is 5 times u2 plus v times u3, which is -10 times u3. Next, let's look into the Gram-Schmidt orthogonalization process. The Gram-Schmidt orthogonalization process can be used with this inner product to produce an orthonormal basis. However, if an orthogonal basis is all that is required, the Gram-Schmidt process can be adapted in the following way. Let A be a basis for a vector space V. The set of vectors u1 until un defined as follows is orthogonal. u1 equals to v1, u2 equals to v2 minus projection u1 v2 equals to v2 minus projection equals to v1 times u1 divide u1 times u1, the whole thing times with u1. This applies for the next vectors also. To obtain an orthonormal basis for V, normalize each of the vectors u1 up to un. To normalize, the formula is u1 divide with the unit vector of u1, comma u2 divide the unit vector of u2 until un divide the unit vector of un. Example R3. Construct an orthonormal basis for R3 from the following vectors. Let V1, V2, V3 are orthogonal bases. To construct an orthonormal basis, we have to find Z1, Z2, Z3 using the normalization process. Z1 equals to 1 over unit vector of V1 times V1. We'll get 1 over square root 14 times V1. Z2 equals to 1 divided by unit vector of V2 times V2, which is equals to 1 divided square root 10 times the set of vector of V2. We find Z3 by 1 divide unit vector of V3 times V3 equals to 1 over square root 65 times the set of vector of V3, which is 2, 5, 6. We get the square root of 65 by the summation of the squares in the V3. Then Z1, Z2, Z3, which is 1, 2, 3, 3, 0, 1, and 2, 5, 6 is an orthonormal basis for R3. Example 4. This example shows how to construct orthonormal basis from a set of linearly dependent vector. The set 1, 2, 0, 3 and 4, 0, 5, 8 is linearly independent in R4. The vectors form a basis for a two-dimensional subspace V of R4. Construct an orthonormal basis for V. The solution is, let V1 equals to the first set of vector and let V2 equals to the second set of vector. We now use the Gram-Schmidt process to construct an orthogonal set which consists of U1 and U2 from these vectors. Let U1 equals to V1, which is 1, 2, 0, 3. Let U2 equals to V2 minus the projection of V2 equals to V2 minus V1 times U1 divide U1 times U1 times U1. We'll get 2, negative 4, 5, 2. That is the set of vector for U2. The set 1, 2, 0, 3, 4, 0, 5, 8 is an orthogonal basis for V. Check that the dot product of each pair of vectors is indeed 0. Compute the norm of each vector and then normalize the vectors to get an orthonormal basis from the orthogonal basis. So we get the unit vector of the first vector, which is 1, 2, 0, 3 equals to square root of summation of squares 1 square plus 2 square plus 0 square plus 3 square, which is equal to square root 14. The second unit vector is square root of 2 square plus negative 4 square plus 5 square plus 2 square, which is equal to square root 49 equivalent to 7. Therefore, the orthonormal basis for V are, first bracket, 1 over square root 14, 2 over square root 14, 0, 3 over square root 14, and 2 over 7, negative 4 over 7, 5 over 7, and 2 over 7. These two vectors are the orthonormal basis for V. Those were the definitions, theorem, and examples for orthonormal basis. And here we have attached the books and web pages that we used as reference to complete our assignment. In mathematics, particularly linear algebra, an orthonormal basis for an inner product space V with finite dimension is a basis for V whose vectors are orthonormal, that is, They are all unit vectors and orthogonal to each other. Under these coordinates, the inner product becomes a dot product of vector space. An orthonormal set must be linearly independent so that it is a vector basis for the space it spans. Such a basis is called an orthonormal basis. The simplest example of an orthonormal basis is the standard basis for Euclidean space. The vector is the vector with all zeros except for a 1 in the ith coordinate. Thank you.
Beautiful, 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 beautiful angel. Love your